Welcome everybody to our 11th learning workshop. This time we'll be covering naming and drawing carboxylic acids and esters as well as their reactions. We'll also try to hit up naming and drawing amines and amides as well as their reactions. So first things first, I'm going to go ahead and zoom this in a little bit. You may or may not be able to see the zoom if you're watching the video. So basically, if we look at this first substance, you can see it's a 2-carbon carboxylic acid. And there's both IUPAC and common names that you'll sometimes see used for some of these short chain acids. And so we're going to actually use both. But in all likelihood, you're mostly really just going to be expected to know the IUPAC name. Now, with the two, what is the ending for a carboxylic acid? Do you know?
An oic acid?
Yeah, it's oic acid. So normally this is the ethane because it's a 2-carbon chain, but because it has a carboxylic acid group, it would be ethanoic acid. Ethanoic acid. Now there's actually another name that you could call it. This would be its common name, and that would be acetic acid. And acetic acid is basically vinegar. You might have heard that name before, acetic acid. It's basically vinegar. Okay, so for the 4-carbon, for the next one, what I first like to do is identify the number of carbons in the chain, the longest number of carbons in the chain, but you have to include the carboxylic acid group. And then I circle the longest carbon chain. And if there's anything that is not part of that longest carbon chain, as is the case with that little branch down here, that's going to be a substituent. So just as you mentioned before, this is going to be, well, the root name is going to be butanoic acid because it's butane, because it's 4-carbon chain, but because it is an acid, we're going to call this butanoic acid, butanoic acid. However, there is a branch here. There's a branch next to this thing. And so we are going to have to indicate where that branch is. We start numbering it from the side closest to the branch. So this would be carbon number 1 right here. So this would be 1, 2, 3, and 4. So 4 carbons. And the branch, the 1-carbon branch, and appears to be on carbon number 2. So in that case, then we would add the 2-methyl to this butanoic acid. So 2-methyl butanoic acid. Now the common name is actually going to be very similar to this. The only difference with the common name is that instead of calling it butanoic acid, we call it butyric acid. It could be 2-methyl butyric acid. And this comes from the fact that this acid is actually an acid that was isolated, or can be isolated originally from rancid butter. Rancid butter, when butter goes bad, you smell that kind of unpleasant spoiled butter smell. That's butyric acid or butanoic acid. Butter, butyr, yeah, that's where it kind of comes from. Okay, now we can look at the next one. Once again, isolate our longest carbon chain. In this case, that'd be 3. And then of course we have 2 branches. We have this one and this one. We number it 1, 2, 3. What would this be called? What would the IUPAC name for this one be?
1,2 dichloro. Uh, I forgot 3.
Propane.
Okay. I was gonna say try.
Mhm. You're close. Where are the chlorine groups? Are they in carbons 1 and 2?
2 and 3.
So this would not be 1,2 dichloropropanoic acid. This would be 2,3 dichloropropanoic acid.
Cool.
Now the common name, like I said, once again, it's very similar. The only difference is that with the common name, instead of being propanoic acid, it's propionic acid, which honestly it's not that different, but dichloropropanoic acid. Propionic acid. Okay. Now I want to give you a shot at doing one on your own. Why don't I have you go ahead and take a shot at number 5. Number 5 is another carboxylic acid one. Let's take a shot at number 5. I'm going to give you a little bit of time to work that one out. Question, or do you think you have the answer?
I wrote something down.
Okay. All right. We'll give just a little bit more time for Frank and Linda, and then we'll go over it.
Okay.
All right, let's go over it. All right. So the first thing that we do is identify the longest carbon chain, and how many carbons did you get for that?
I got 6.
Mm-hmm. So it would be 6. And this is a 6th one here. So in that case, the root name for this would be what?
Hexanoic acid.
Uh-huh. All right, so hexanoic acid, and it looks like we have a few substituents, right? Yes, Frank, you had a question or comment? Oh, okay. So we got 1, 2, and it looks like we have 3. So hexanoic acid is the root name. What would we give the hexanoic acid? What would we do about the branches? What would I call that?
I put 2,5-trihexanoic acid.
Okay, so first of all, are all of those 3 branches the same?
Oh, no, they're not. So I'm wrong.
So what is the name of the branch that's closest to? Well, yeah, let's go ahead and number the carbons because that's always a good idea first, right? So,
Okay, so
all right, and so what is that 2-carbon branch called?
ethyl.
Ethyl, very good. And what is the 3-carbon branch called? I mean, the 1-carbon branch,
Methyl.
methyl. So we have 1 ethyl and 2 methyls.
So it's 2-ethyl 5-dimethyl hexanoic acid.
Very close. Remember, we have to give a number for each methyl group, even if they're on the same carbon.
So 5-5?
Yep.
Oh,
2
wow.
ethyl dash 5 comma 5 dash dimethyl. 2 ethyl 5 dimethyl hexanoic acid. And I'm actually going to put this up here just because this is such a long name. It kind of is getting in the way of everything else. So 2-ethyl-5,5-dimethyl hexanoic acid. And with this one, you wouldn't really be expected to know the common name, so don't worry about it. All right. Let's take a look at some of these esters. Esters are a little bit different. Esters are actually very much like ethers when it comes to how you name them. One of the things that I like to do with esters and ethers is to separate it based on each side of the oxygen, okay? So there's two different sides here, okay? There's the left side of the oxygen and the right side of the oxygen. Now, which side is more important? Which side is more important?
Left side?
Yeah, the left side, the side with the double bond O, right?
Yeah.
So it's not actually about how large it is, it's about which side has the double bond O. So this more important side is going to get the ending proper to an ester. So an ester, you name the less important side first as a branch. So a 1-carbon branch, this would simply be called methyl, right? But the more important 3-carbon side gets an O8 ending. And so this is 3 carbons, so this is going to be propanoate. Propanoate. And so I would actually simply name this methyl space propanoate. Normally we don't put spaces in names, but with the ethers, with the esters and with the ethers we do. At least if you're naming ethers with the common naming system, or the esters, even with the IUPAC naming system, you separate it. Now the only difference between the common name and the IUPAC name for this is that, once again, that propanoate is going to become propionate. So it'd be methyl propionates. Okay. And as I said before, there's not really anything you have to worry about with a common name for a 6-membered ring. I think there actually is a common name for it, but it's the common name, shall we say, is not that common. So you don't have to worry about it. All right. Now let's take a look. The next thing that we can do is look at number 6. Okay. So this is one that actually has a branch in it. Once again, we're gonna circle the more important side and the less important side. There's the two sides of the oxygen. Which side is more important? All right, you're both in agreement. It's the left, absolutely. And the left has how many carbons? This is 1, 2, 3, 4. Yep. In the longest chain, but there's also this one too. Okay. Now the tricky and goofy thing about this is that the more important side, you can do this with the less important side too, and when you get complex substituents, but I don't think you're going to have to end up dealing with anything like that. But you may get a substituent on your more important side, in which case you could number it like this. If this is 1, carbon number 2, carbon number 3, carbon number 4. All right, and so this 1, 2, 3, 4, and I have this little branch here. It's a 1-carbon branch. All right, so if I'm going to name the left side, the more important side, if I was just naming that side, what would I call that? 2-methyl what?
2-methyl propyl. or propane?
Well, it's not 3 carbons, right? It's 4.
Oh, sorry, I meant, yes, I'm thinking 4 and I said 3. So 2-methyl bupanoate?
2-methylbutanoate. Absolutely, that's 100% correct. So 2-methylbutanoate. And then what would I put for the less important side? What would I call that?
Ethyl.
Yeah, exactly. It'd just be a substitution. So ethyl. And so the full name for this is going to be ethyl space 2-methylbutanoate. And that's actually another reason why we space this the way that we do, because the truth of the matter is that the space helps to differentiate between what's on one side of the oxygen and what's on the other side of the oxygen. Because both the part on the other side of the oxygen is named like a substituent, and this methyl is named like a substituent. Okay, let's take a crack at number 7. Let me have you try to name that one. And you can raise your hand when you have an answer, or you think you have an answer. Okay, see. Let's go ahead and take a look at it then. Linda, you okay if we go ahead to it?
My girl, I don't know it. I'm
That's
sorry.
okay. That's okay. That's what we're here for. That's here to go over it and hopefully make it have it make a little bit more sense. So the first thing is, let's identify the two sides of this thing. Now, here's the question. Which one of these sides is the more important side? The right or the left? The right. So what did you get for the name for that part, Mia?
I don't know if this is right. I got methanoate.
That's right.
Oh my gosh.
Anyway, that's what you'd have to put, because I mean, you really don't have another choice, unless you use the common name. Now, what? So in that case, that means the other side is going to have to get named as a substituent. Well, 4-carbon group named as a substituent, what would you call that?
I just put butyl.
Mm-hmm. So this is butyl, 4-carbon group, butyl. And like I said, sometimes it helps if you want to just mark the presence of the carbons with the little dots or whatever. For me, I know that that kind of helps keeps track of how many you have. But yeah, so it's butyl. And then you have the methanoate. So the IUPAC name for this is actually very simple. It's just going to be butyl methanoate.
Yes.
Alternatively, common naming methanoate, you don't say methanoate, you say formate. So it would be butyl formate. This actually comes from the Latin word for ants. An ant in Latin is formica. And for the common name for a 1-carbon acid is formic acid, because ants, if you shall I say, if you know get bit by an ant, it burns. Like it says fire ants, you think fire ants, um, it burns and it stings because of the acid that's present in their bite. And so formic acid is the 1-carbon carboxylic acid that ants have. And then of course, if you extend that name formic acid to other things where there's a 1-carbon, it'd be formate. Um, if it's connected, like in an ester, so to speak. Okay, cool. So now, number 8 is a unique type of acid. Whenever you have a benzene ring attached to a functional group, a lot of time ends up having kind of a unique name. Well, and this is not too fancy or anything like that. It's not cyclo because it has a benzene ring. It's those alternating double and triple bonds you see here. Double bond, double bond, double bond. So double bond, single bond, double bond, single bond. You have alternating double and single bonds. That's in a six-membered ring that's called benzene. But when it's connected to functional groups, sometimes it gives different names. It's connected to an alcohol, we call it phenol. Connected to an NH2, an amine group, we call it aniline. But the special name for benzene attached to a carboxylic acid is actually pretty simple. It's just benzoic acid. So the benzoic acid. Now, of course, you also have to include the substituents, and as you might guess, you're going to start your numbering from the carbon that has the attachment to the benzoic acid group or the acid group. So that's going to be number 1, and then you'll number it in such a way as to give you the lowest numbers. So I have 1, 2, 3, the chlorine are 2 and 3. So this, in fact, is going to be not simply benzoic acid, but 2, 3 dash dichloro benzoic acid. Now let's move that over a little bit. 2,3-dichlorobenzoic acid. And once again, common name is the same for benzoic acid. There's no difference. And once again, I don't know exactly how much your professor is going to expect you to do with the common names, but now, Leanne, you got the last ester correct, so that's awesome. Do you guys want to maybe give number 9 a shot on your own, or do you think you know enough you can just skip that? What y'all decide. You want to practice one word, or you want to skip it?
I'd like the practice.
Okay, let's go ahead and do number 9 then, and you can go ahead and raise your hand when you think you have it. What do you think, Linda, Frank? Have an idea? Ready to go over it?
I think we should go by it. I'm just lost. That's the truth. I'm not even making any effort.
Oh, what would you say? I'm sorry.
I said I think you should go ahead. I'm just lost. I don't know what to do.
Sure, no problem. Okay, so the first thing, we'll go ahead and identify our carbons. 1, 2, 3, 4, 5. And then we also have one over here. It's always helpful to identify your carbons. I'm going to go ahead and circle each side. One side of the oxygen, the other side of the oxygen. And what did you get, Leanne, for your name?
I got methyl pentanoate.
Excellent. What did you get, Frank? You get the same?
Yeah, same.
Awesome. Yeah, methyl on the less important side. The more important side, the one with the double bond O. That is going to be the O8 ending. It's 5 carbons, so pentanoate, methyl pentanoate. Awesome. Pentanoate. Okay, just going to do one quick. I think writing these is actually easier than drawing. So I'm going to go ahead and do quick number 4 and number 6, or actually I'll do number 4, and then I'm going to have you do number 6. All right. So if I was to draw 4, it says 3-ethyl-2,2-dimethylpentanoic acid. The first thing I always want to do when I'm actually drawing substances that I'm given a name for is start with the root name, pentanoic acid. So I know that this is going to be, I'll have a double bond O and a single bond OH because it's a acid. And I know I need 5 carbons, so there's 1, 2, 3, 4, 5. Pentanoic acid. Here's my pentanoic acid. But then it says there's 3 ethyl. So on carbon number 3, I'm going to put a 2-carbon branch on it. I'm going to change the color. And actually, I may just go ahead and number these carbons first. 1, 2, 3, 4, 5. And so, okay, I'm going to go ahead and then put my branches on it. On carbon number 3, I have an ethyl group, so that would be a 2-carbon branch. 1, 2. There's my ethyl group. And then it says 2,2-dimethyl, so I would put 2 1-carbon methyl groups on it. You could also show it with the condensed structural formula if you wanted to do a C double bond O OH. And then you could just do, okay, well, I'm going to do 1, 2, 3, 4, 5, because it's pentanoic acid, carbon. And then I know I have a 3 ethyl, so I'll just do a CH2, CH3. That's an ethyl group. And then I have 2,2-dimethyl, so I know I need 2 methyl groups on carbon number 2, so CH3, CH3. There you go. And so this is going to be a C. There's not going to be any H on the carbon right next to the carboxylic acid because it already has 4 bonds. There will be 1 H on carbon number 3, 2 H's on carbon number 4 because it only has 2 bonds, and then the last one, carbon number 5, is going to have 3 H's attached to it. So that's another way you could write that compound if you wanted to. I like to sometimes use the bond line structure, the one on the right, just because it's a little bit quicker, a little bit easier. Go ahead and find a spot on the board and actually here, I'll even write a little initial for you. Oh. There we go. And all right. Go ahead and draw what you think number 6 would be to the best of your ability on the paper. I'll give you a little time to do this. If you feel comfortable doing it. If you don't want to, you don't have to, but go ahead and give you so this is a spot for one person, this is a spot for another person, this is a spot for the other person. Each of you have a spot.
Okay, so that's what I got. I don't know if you can make it out.
Let's take a look.
One, two, three, 4, 5, 6, 7. Got my bromine there on 2, and then my ethyl on 3.
Okay. 1, 2, 3, 4, 5, 6, 7. Yeah, very good. So 2, 2, oh, okay, so this is 2,5-dibromo, and you had 2 and 5, and 3 ethyl, and you did that well, absolutely. And it looks like, yeah, awesome job, Frank. Excellent, well done. You nailed it. Both of you did excellent. Okay. Well, let's go ahead and take a look at some of the reactions now. The reactions with this, with these groups. let's see, I'm going to share. No, share file. Okay. Now, with the carboxylic acid, hydrolysis is just a reaction with water. So lysis means splitting, so hydrolysis is water splitting. I guess you can think of it like that. It doesn't necessarily always split water though, and so I'll show you what I mean by that. As an acid, as you may remember from earlier on, an acid is a proton donor, and a base uh, uh, was going to be a proton acceptor. So an acid, um, so base essentially what you're going to do here is you're just going to donate this hydrogen from the carboxylic acid to the water, and so that's going to end up giving you this O minus here, which is the conjugate base of the acid, and then you'll also get an H3O plus, which makes sense because when acids are in water, they do form an H3O plus. Okay. So then we're going to look at a similar reaction, neutralization. Neutralization does something very similar, except that instead of ending up with an H3O plus, the OH minus here is going to actually rip off that hydrogen, neutralize it, and form water. So with a neutralization reaction, you get the deprotonated acid, just like hydrolysis. The only difference is a lot of times, since you have that sodium ion, that Na is going to be a positive charge, so it's going to go with this. It's going to go with that deprotonated carboxylic acid in the form of salt. Okay, but then you'll also get water because the OH from the OH basically from the NaOH and the H from the acid come together. So the OH and the H come together to form water, and then the sodium just sticks itself to that carboxylic acid. Does that make sense?
One question.
Sure, go ahead.
Are you always trying to stick atoms that turn into water like as a priority, or do you search for like trends? Like is trying to find water the first thing you try to do in these types of reactions?
I think the key thing is to recognize the nature of the acid as an acid.
Mm-hmm.
As an acid, the acidic hydrogen is going to tend to donate itself to give itself to something else. And
Okay.
then you just have to ask yourself, okay, so well, what is it going to give itself to? If it's water there, it's going to give it to water. If you got OH, it's going to give it to OH. It's going to give itself to the strongest base that there's present, but in this case, you're not going to get multiple bases. You're just going to see the one thing that is offered to it, so to speak.
Okay.
And so here's another neutralization and hydrolysis, but I also want to go through another very important reaction with carboxylic acid, and that's called esterification. And esterification is the formation of an ester. And this is a really interesting reaction. So you're gonna have to unfortunately memorize this one. But effectively, what you can think of as what happens here is this. You get the OH from the carboxylic acid and the H from the alcohol come together and form water. And then the other two pieces stick together. This oxygen, whoa, I don't want that. This oxygen comes back and sticks itself to that C double bond O. So the H and the OH come off and form water. And the oxygen from the alcohol comes and sticks itself to that carboxylic acid carbon, or the carbonyl carbon. And you end up getting this product. So you end up getting, you know, C. I'm just going to draw the C's because I'm lazy. I don't want to draw the H. So here's your carboxylic acid. Okay. And then you have from the alcohol, you have the oxygen, the carbon, carbon, and carbon. You see in this case there's 3 carbons with that alcohol, right? And you notice the number of hydrogens actually don't change here, so I will actually draw them on the carbons. You have the CH3. This is going to be a CH2. On the alcohol, you have a CH2, and you have a CH2 and then a CH3, right? There you go. So basically, that's what happens. The ester comes together. I'm going to show you one more example, but then I'm going to have you do an esterification one, okay? So I'll show you this example, and then we'll go back to the other one. I think that that'll be a good one for you. So in this case, the principle is the same. I know it looks a little bit more intimidating, but it's really not. So once again, you see your carboxylic acid group, the hydrogen from, or the OH from the carboxylic acid. Ah, what am I doing? There we go. The OH from the carboxylic acid and the hydrogen from the oxygen, or hydrogen from the alcohol, come together and form water. So then the other two pieces stick together. This oxygen here, keep forgetting I'm on the shape thing. The oxygen from here is going to come and stick itself right to that carbonyl carbon. So what's attached to it, really not all that important. So here's my benzene ring from the benzoic acid. I have my double bond, single bond, double bond. I have my 2 chloro groups, chloro. And then I have my C double bond O. I lost my OH. Instead, the oxygen from the other group comes and attached to it. Now that oxygen is connected to a carbon here, and then that splits into these 2 carbons. So the oxygen is connected to a carbon that splits into 2 other and is 1 carbon on each side of that split. And so that's all you do. Stick it together. You now have the ester, and of course you also have water, right? Did that make sense? Did you follow me there? All right. Let's go ahead and take a shot and have you do. Let's have you come up with the product for number 6. Let's have you do number 6. Draw that product. Cool. All right, Frank, you want a few more seconds or should we go over it? What do you think?
No, I'm good.
All right. So you should have, I'm going to do a bond line structure. Recognize that the OH from this is going to leave. H from the other one's going to leave. And then the oxygen here sticks in the end of here, the carbon. So I have a C, whoops, C, double bond O, and then I have 1, 2, 3, total of 4 carbons there. And then I have an oxygen, and on the other side I have 1 carbon here, 1 carbon here. And then of course the appropriate hydrogens. Is that what you all got? No! You're supposed to always get things right. Man, I count on you. Does that make sense how you would get that though? Did you see it? Okay. So I think the key thing is to recognize that this piece right here is this piece right here. Okay? I'm adding the alcohol. I'm just taking off the OH from the carboxylic acid and I'm adding that to the other side. I have to flip it over so that the oxygen's facing the opposite side. But that's the piece that I'm doing. Do you see it now? Does that make more sense? It's okay if it doesn't. Okay, cool. I feel like I want to give you another shot at that. So let me have you do problem number 12 on page 2. I switched it over to page 2. Let me have you do problem number 12 on page 2. Okay, no problem. Oh, okay, so you already drew it. Okay. How about you, Frank? Are you got it? Okay. So that is very close to the correct answer, but it's not quite the correct answer. At least I think. Yeah. So you definitely have the right idea. Not sure who drew it, but yeah, we have the 1 here, 1 here, 1 here, and 1 here, right? And then of course we have this carbon here. 1, 2, 3, 4, 5, 5 carbons. But over here with this alcohol, this is actually a carbon, a tertiary alcohol, carbon that's connected to an oxygen, it's also connected to 3 other carbons. So basically, if I rip off that, if I rip off that OH from the carboxylic acid group, and I take off the hydrogen from the alcohol, then I'm going to go ahead and put this back right onto the end of here. And so it's 1, 2, 3, 4, 5, 6. Unfortunately, it looks like the number of carbons in that structure was wrong. And Ah, there's two people joining. Yay. Yes, I'll wait for the explanation for just a moment. Hello. It looks like, unfortunately, your answer was not quite right. This only had 5 carbons if you look at this. 1, 2, 3, 4, 5. And if you only have 5 carbons, it's not going to, unfortunately, do anything, right? So, or it's not going to be 6, as you've shown. So, what's going to happen here is you will get your C double bond O here, and the carboxylic acid is going to have those 5 carbons, 1, 2, 3, 4, plus that initial one. So 1, 2, 3, 4, 5. And on the 4th carbon, there's a chlorine. And yeah, and that's it. On the 4th carbon, there's a chlorine, and that's it. And then on the other side, yeah, this is 1, 2, and then of course this is 1, 2, 3, 4, 5. On the other side, you're going to have that alcohol, and of course the alcohol group, I'm going to go ahead and change the color to red to distinguish it from the other. You have the oxygen there, but then you have to recognize, okay, so it's bonded to a carbon, but that carbon is bonded to 3 other carbons. So I have to put all 3 there. It looks like only 2 are shown. Does that make sense? Cool. So now let's go ahead and take a look at the opening reactions of hydrolysis. So these hydrolysis reactions here, and basically the hydrolysis is the opposite of esterification. It's the breaking apart of an ester. So let's start with one that's really simple. Let's start with like number 8. So this is a hydrolysis reaction. I'm going to be splitting the ester, and essentially what's going to happen here is I am going to, I can cut, and you can think of it a couple different ways, but remember how we took off the OH and the H of the OH of the carboxylic acid and the hydrogen of the alcohol? We're going to do something similar, except instead of taking off the H of the alcohol and the OH of the carboxylic acid, I'm instead going to cut this in 2 pieces, like this. And I'm going to add a hydrogen to the less important side, and I'm going to add an OH to the more important side, the one with the carbonyl. And that will give me my alcohol and my carboxylic acid. So this is going to be 3-carbon group with a carboxylic acid at the end. And then I'm going to also get 1-carbon alcohol, CH3OH. So let's do another example with the, well actually, you want to go through 9 together, or do you want to do it on your own? Okay, so go ahead and show me where you would cut that. Go ahead and show me where you would cut that. Draw a line. Yeah, that's exactly right. Cut it right there. So which side would get the hydrogen?
The left side. The right.
The
Sorry, I still haven't had my coffee yet.
That's okay. Yeah, the right side would get your hydrogen, which means the side with the double bond O gets your gets what? The other side's gonna get your what?
OH? No.
Okay. Yep, it's gonna get your OH. So here we go. Now I'm going to go ahead and draw my products. I have a 4-carbon carboxylic acid because if I look at this, this is 1, 2, 3, 4 carbons here, and then also there's a branch on the second carbon. So I'll go ahead and draw that. 1, 2, 3, 4 carboxylic acid. And then I have the branch on carbon number 2. Then I also have that 2-carbon alcohol. And everybody's happy. Essentially, both sides end up with an OH on them. In fact, if it's easier for you to see it this way, you can simply cut both sides on that oxygen and just add an OH to both sides, if that's easier. See, I'm going to leave the oxygen in the middle alone. I'll just cut both sides and add an OH to both sides. And you get the same thing. Mechanistically, that's less correct, but it still works to get you the product. So that's acid catalyzed hydrolysis. For base catalyzed hydrolysis of an ester, you basically, no pun intended, do the same thing. You're going to go ahead and cut it between the carbonyl and the oxygen. The only difference here is that since I'm adding OH instead of H2O, the H goes to the alcohol side, and instead of getting an OH on my carboxylic acid side, I'm going to get an ONA. So the side with the double bond oxygen is going to get an oxygen with an Na next to it. And then the other one is you have this 4-carbon group here with the OH, or with the oxygen there. So that's going to be 1, 2, 3, 4, and then OH. You always get the alcohol, but with the carboxylic acid with base catalyzed hydrolysis with the OH, instead of getting the OH, I end up getting the ONA. Or if I have KOH, it'll be OK. It's going to be okay. It'll be okay. So you want to give the next one a try? You can let me know when you have it done, and then we'll go over it together. You don't have to draw it. Yeah, just raise your hand when you think you have it done, and then we'll check it. All right. Let's take a look at this. So this is what we're going to have here. The first thing is we identify where we're going to cut this, cut it in between the carbonyl and the oxygen. And then once we've cut it between the carbonyl and the oxygen, then we can go ahead and break it apart into its two pieces. Of course, it's base catalyzed hydrolysis. The alcohol is going to remain intact, which means this piece here on the side without the carbonyl is going to get an OH. It's going to get the H. The other side is going to get the OK. Okay. So then I just have that 2 carbon with the OK. And then I have the alcohol. And that's pretty much it. Easy peasy. Now you could also put the plus sign for the potassium ion and the minus sign for the oxygen ion, but it's not entirely necessary. But that's just one. You could do it. Does that help? Okay. How about you, Leanne? Did that make sense? Did you get that?
For some reason, my writing board's not working. I don't see what you're writing. It's just, it kind of puts your lines in weird places on my page. So I'm not sure.
Oh, really? That's so strange.
Yeah, so I've just been
Um,
listening. I can't really see
you
anything.
know what? I'm sorry. Let me go ahead and I am going to go ahead and stop sharing it and let me try to reshare it. And in fact, I'm going to go ahead and skip to the naming of and drawing of amines and amides because I think that's going to be the next thing we really want to touch base with real quick. Now we don't have a ton of time, so if it's okay with you, I might just kind of go over several examples to just kind of give you a better idea how to do this. Um, and yeah, so I mean, let me go ahead and do it as a best fit actual size. Here we go. All right. So you tell me if this works, okay? So for the first amine, this is actually amines are named very similar to, in the common naming system, named very similar to ethers. I identify the 2 sides of the amine, and then I just label each side as the substituent, and then add the word amine at the end. Now the only difference here in the common naming system, the only difference here is that I don't put any spaces in between the words. For ethers, I put spaces in between them. For for amines, I don't. So this would, and I would put them in alphabetical order. So this would just be ethyl, methyl, amine. No space. No space. Does that make sense? Can you see that? Is that showing up in the right spot? Awesome. Now, alternatively, an alternative method of naming this, I'll show with the red marker, is to circle the longest carbon chain that has the nitrogen attached to it. The longest carbon chain with the nitrogen. If there is a group attached to the nitrogen, if there's a branch attached to the nitrogen, I am going to give it, instead of giving it a number, I'm going to give it a letter. I'm going to call it N. So in this case, the IUPAC name for this would be N-methyl ethan, and then the ending would still be amine, ethanamine. So N-methyl ethanamine or ethyl methylamine. In either case, no spaces. Does that make sense? Any questions on that? Okay, cool. Now, as far as the classification, when the nitrogen is attached directly to 2 carbons, it's secondary. If the nitrogen is attached to 1 carbon, it's primary. If it's attached to 3 carbons, it's tertiary. So this is a secondary amine. Then I'll go ahead and look at the IUPAC naming for the next group. Once again, I'm going to go ahead and circle the longest carbon chain, or rather, if for IUPAC, for the common naming, I'm just going to do each side and treat it as a branch. Each one of those is a 3 carbon branch with a split. So that would be isopropyl. So I'm going to actually just call this, for the common naming, just 2 isopropyls. I'm just going to say this is diisopropylamine. Diisopropylamine. That's it. And then classification. Once again, this is a secondary. And as far as the IUPAC name, I would treat one of these sides as more important than the other. So with the IUPAC name, even though they're technically equal and exactly the same, I'll treat one as more important than the other. So the less important side, or the one that's attached, not circled, basically would be treated like a branch. So that would just be called isopropyl, just like before. But the other one, I have a chain. It's going to be a 3-carbon chain. And since the nitrogen is attached to carbon number 2, I would call this N-isopropyl dash 2-propylamine. N-isopropyl 2-propylamine. So it's a 3-carbon chain with a nitrogen attached to it. The nitrogen is attached to carbon number 2, so that's why I call it 2-propylamine. Now, I did not have to put the number for the 2-carbon one previously, the ethanamine, because it wouldn't matter which carbon that nitrogen was attached to. It would still be attached to carbon number 1. But with a 3-carbon one, it can be attached either at the end or at the middle. The nitrogen can be either attached at the end carbons or in the middle. So let's do, number 3. So the common naming system, once again, I have two sides to this. And I'm going to go ahead and change the colors. And then we also have a 1-carbon branch. So the 4-carbon branch is going to be a butyl group. The 1-carbon branch is going to be a methyl group. So this is going to be common name butyl methyl amine. Butyl methylamine. Oh, and I made a little mistake in the previous one. For the common name, I should not have put any sort of space. So I took out the space there, as you can see. So butyl methylamine. And these substituents always get labeled in alphabetical order. Now, if I was to do the longest carbon chain that's attached to the nitrogen, here we go. Now that's a 4-carbon chain, and I'm going to start numbering from the side closest to the functional group, closest to the nitrogen. So this is carbon number 1. This carbon, that's going to be number 2. This carbon over here is going to be number 3. And the other one's going to be number 4 over here. So this is going to be a 2-butanamine. 2-butanamine. And forgive me, I did make a little mistake with the previous one. I put propylamine. I should have put propanamine. With the IUPAC name, I do not use the substituent name. So propanamine, N-isopropyl 2-propanamine. And for this one, I'm actually going to type it up in the top so I have enough space. So this would be N-methyl 2-butanamine. Sorry for the mistakes there. But does that make sense? Any questions on those? Okay. Okay. So It does make sense, right? Or does it not make sense? Oh, it makes sense. Okay, good. All right. So then I just want to show you the naming of the amides. Now, chances are you are not going to get any complicated amides, but I'll show you how to do the amides. It's actually pretty simple. I'll go through example 8 and example 9. Most of the time, you're going to get something like 8. And number 8 has this one here, and of course you have this carbon here. So a 3-carbon chain. So that root name there is then going to be propanamide. Propanamide. Yeah, propanamide. But now we also have CH3, Cl, our branches off that main chain. So the main chain, gotta get rid of that, sorry. So I'll go ahead and circle this. So I see I have chloro on carbon number 2 and a methyl on carbon number 2. So this is real simple. It's just going to be 2-chloro-2-methyl propanamide. And once again, no spaces. Even though when an ester you have spaces, with amines and amides you don't. Ethers and esters can have spaces. Amides and amines don't. Otherwise, they're very similar in their naming. And we won't worry about the common names for amides. Now, I do want to do one more, number 9. I know we're getting a little bit late, but I do want to go over just this one more because I want to show you what happens if you have carbons attached to that nitrogen. So I have the nitrogen here. I have this amide group. It's the 2-carbon amide. So this is going to be ethanamide. Okay? But ethanamide is the root name. But then, now I'm going to have a methyl group here and a methyl group here. I have 2 methyl groups, and they're both attached to the nitrogen. Now, since they're attached to the nitrogen, they're not going to get a number, but they are going to get a letter. So this is going to be N, N, dimethyl ethanamide. So NN dimethyl ethanamide. Does that make sense? NN dimethyl ethanamide. Cool. So that's pretty much all you have to do. And the reactions with amines and amides, I was hoping we'd have time to go over that, but we seem to have run out of time. But I do want to just kind of show you it real quick. Reactions of amines and amides. You're going to have a similar type of situation, except that with amines, they tend to be basic rather than acidic, so they're going to take, like the carboxylic acids, they're going to split water, but it's going to take a hydrogen rather than, this is going to take a hydrogen. So you're going to get a hydrogen attached to the nitrogen here, and then this would turn into an OH. And with an HCl, with an acid, once again, you're going to get a hydrogen attached to the nitrogen, giving it a positive charge. Positive charge. And the other thing you're going to have is the Cl with the minus charge. by itself. So, and then of course neutralization. Yeah, so neutralization, hydrolysis, they're going to be a little bit different, but somewhat similar. You can also get the amidation reaction, which is basically the same type of reaction as the esterification. And then of course you can also get the opposite of that, the hydrolysis of an amide, which is basically you split it along those things and you end up getting the carboxylic acid or the carboxylate. The answer keys are posted on the website for each of those. So if you have any questions, please feel free to reference those. Also, please feel free to come into the Science Learning Center and ask any questions you might have on that, because I know that those reactions can be a little bit tricky. Any questions before we wrap up? Sorry, I know it was a little bit rushed at the end. Thank you so very much for coming, and we'll see you at our next session.